Section 5.2, definite integral. So from the previous section, we got to the point to prove that the area under the curve can be found using the limit as n goes to infinity of the sum f of x I, let's call it star, delta x, where I goes from 1 to n. That's the definition of, or the way we found the area. Area under the curve, function f, say from A to B. So that was the area. And delta x was the width of the rectangle. And then we found the sum as a function in n, and then we passed the limit as n goes to infinity. And that actually gave me the exact area under the curve. So we can write that down for x from A to B. We have x is given A to B. We divide this interval A to B into n subintervals with delta x b minus a over n. All this from previous section. Then I'm gonna introduce a definition. We define the integral. See, this sign looks like it's a stretched s. The integral sign of f of x dx from A to B is the limit of the sum f of xi star delta x. I goes from 1 to n as n goes to infinity. So what is this saying? This is read as the integral of f of x from x equals a to x equals b. That's how you read this. This part is called the integrand. A, we call it the lower bound of the integral, and b is the upper bound. Of the integral. So what does that do? Where did that come from? Of course, Riemann came up with this. Riemann, the German mathematician. So what he said if we have a graph like the one I showed you earlier, from A to B, we need to find this area. What we can do, we can simply find the area when we split it into rectangles, all these rectangles, as we did in the previous section. So what he said I can find this part here represents the area of of the rectangle. So that's delta x, and f of x is the height. So that's the area of the rectangle at x equals x. And then he said, if you find the areas of all these rectangles and add them up, so that's what the left hand side means. It means you find the areas of all these rectangles and the integral will sum them up from x equals a to x equals b. And that will give us the area under the curve, the exact area, using that integral sign. So let's add notes to this. Let's add note. First thing, if the limit as n goes to infinity of the sum fxi star delta x I goes from 1 to n, if this limit exists, then we say that f is integrable. On the interval AB. Integrable means we can find its integral, and we will learn how to do that. Second one, when I wrote down that f of x dx, we wrote from A to B. That means from x equals A to x equals B. But I want you to get used to different variables. I don't want you just to see x, x, x the whole time. So we can go, even if it's fw dw from c to d, that means w goes from c to w equals d. So the variable has to match. If we have f of m dm, that means m goes from e to t or something. And at the end, all of them will give us the same number, same value. All will give us the same value. Now, while we are finding the areas under the curve, we can see something good to know before I forget. So let's call it note 3. If we have a curve like this given, let's say a graph goes this way. The area here for this region is A1, area here is A2, area here is A3. One thing to note that area 1, when we calculate area 1 and area 2, both of them will give me a positive value. If I calculate the area 2, will give me a negative value. That doesn't mean we did something wrong when we got a negative area. The negative sign is an indication that the majority of that area falls below the x-axis, if not all of it. So when the graph falls below the x-axis, the area will be negative. The area will be negative. So that's what the negative sign indicates. That's why A2 definitely is going to be negative. Definitely is going to be negative. If we are finding, let's say, we're finding the area for the entire curve that goes like this. So the area of the entire curve, it's a combination of this and this. Like you combine them together. It's a combination. So let's call this A1 and A2. So when we find the area is a combination of A1 and A2. But guess what's going to happen? We expect this to be negative. Since A2 is bigger than, as you can see from the figure, A2 is bigger than A1. So since more area falls below the x-axis, we expect the whole area to be negative. So now we can summarize this as a theorem, what we just wrote up earlier. As a theorem, this is really a theorem. If f is integrable, on the closed interval AB, then the integral from a to b f of x dx equals the limit as n goes to infinity of the sum of f of x I star delta x, where I goes from 1 to n. That's the one I wrote earlier, where delta x is always b minus a over n. And xi from the previous section, it's a plus I times delta x. Very important stuff. So how do we start? By applying this as an example. We can ask to express the limit as n goes to infinity of x sub I square plus 2 cosine x sub I delta x as I goes from 1 to n as an integral on the interval 0 to 2 pi. So it might look difficult to students. Oh my god, what am I going to do with this? Just compare it to the theorem right above it. So what they basically give us, they give us the right hand side of the theorem, and we just need to get the right hand side. So notice this matches this. So the function f of x is, so from here f of x is simply x squared plus 2 cosine x. No need for the I. And then the the right hand side, delta x is just dx. And then what else we have here? What else you see? They give us an interval from 0 to 2 pi. That means from x equals a to x equals b. So then that thing, the limit they give us, can be expressed as an integral of the function f of x dx from 0 to 2 pi. Okay, so that's all we have to do. We need to express it as an integral, and that's what the integral is. Now, while working with this section, there are some properties for the sigma notation we're going to recall here. We're going to be using them. Recall properties of sigma. That's a sum. So what are the properties of the sigma that we learned in the previous course? So the sum of c from I equals 1 to n is cn, because you're adding cn times. The sum of cai, I goes from 1 to n, equals c. You take the c out, c as a constant, ai, I equals 1 to n. 3. If we're doing a sub I plus or minus b sub I goes from 1 to n. You can do the sum a sub I plus or minus the sum b sub I goes from 1 to n. Very important stuff. So now let's see how we put all the stuff we learned together. So let's look at, let f of x be the function defined as x cubed minus 6x. We are going to evaluate the Riemann sum as we did in the previous section. Riemann sum for f of x using right in points. So they're telling exactly which ones to use. And a equals 0, b equals 3, n equals 6. That's the number of sub-intervals. It has to be 6 sub-intervals we're going to be using. So always the first thing I do, I find delta x. b minus a over n. So b is 3, a is 0, n is 6. That's 1/2. That gives me 1/2. So now I'm going to go on a number line just to make it easier for myself. So 0 starts here. I'm going to go add 1/2 every time, then 1, then 1/2, 1 and 1/2, then 2, 2 and 1/2, and then 3. And notice how many of them are there. You can count them. 1, 2, 3, 4, 5, 6 regions. Do you see that? And that's what they wanted us. They wanted us to have 6 sub-intervals. So I got these points, and you can write these as decimals or fractions. You can write this as 0.5, 1.5, 2.5, or keep them like so. So the right endpoint, I'm going to use r sub 6, means I'm using right endpoints for 6 sub-intervals. And this is the sum of f of xi delta x. I goes from 1 to 6. This is, we start, since it's the right endpoint, we skip the first one. We don't touch the first one. I need 1, 2, 3, 4, 5, 6. 6 of them. I don't need the first one because it's the right side. So I start with the first, the f of 0.5 times delta x, f of 1 times delta x, f of 1.5 times delta x, then f of 2 times delta x, plus f of 2.5 times delta x, plus f of 3 times delta x. Then we can factor delta x out, right, which is 1/2. So take 1/2 out. That will make it f of 0.5 plus f of 1 plus f of 1.5, and this goes on and on until f of 3. And I'm sure everyone can put that in the calculator. Remember, the function is given to us, x cubed minus 6x. Substituting that in, that will give me r sub 6 to be about negative 3.9375. Notice how I got a negative. Doesn't mean it's wrong or something wrong. It means the majority, if not all, the curve falls below the x-axis. Okay, falls below the x-axis. Part B. So it's asking us to evaluate, in this part, evaluate the integral from 0 to 3 of x cubed minus 6x dx. So we need to evaluate this. Okay, so evaluating something like this requires us to use the theorem that we were given earlier. So how we use that theorem to evaluate this? Well, the first thing I'm going to write is 0 to 3 x cubed minus 6x dx. Using the theorem, is the limit as n goes to infinity of the sum of what? F of x sub I delta x. I goes from 1 to n. Remember? So how do we go about this? We need to find what delta x is. On the side, we can find what delta x is. So I'm going to do it here. Delta x is b minus a over what? Over n, because I don't know how many subintervals. So I'm going to do it n subintervals. That's delta x. So always the first value we start with, remember 0 to 3, that's x sub 0. X sub 1 is 0 plus 3 over n. X sub 2, you add 3 over n every time. X sub 3, 9 over n. And this keeps going on and on with this, all the way to x sub I. What is the ith position? Notice how they all on the top, like 3, 6, 9, all of them are multiples of 3 over n. So it's 3i over n. 3i over n. So what do we need that for? So let's see. The limit as n goes to infinity. That gives me, first thing, the f of xi. So f of 3i over n. Okay. The next step is, keep the sum for now as is. We need to find what f of 3i over n is. They give me the function. This was the function. So I'm going to substitute 3i over n to the third power minus 6 times 3i over n times delta x. Delta x is 3 over n. Now, limit as n goes to infinity. Let's put 3 over n here in the front. And we have the sum I goes to 1 to n, and 3 cubed is 27 over n cubed I cubed minus 18 over n I. And we're going to evaluate this. Like, we're going to see how to evaluate this. The first thing, remember, this sum is being summed over the values of I. Values of I equals 1, 2, 3. So what we need to do in this case is that keep this the same, take the 27 over n cubed out, and just keep the I inside. I equals 1 to n minus the sum of the other one, which you take the 18 over n out, sum of I equals 1 to n. So that gives me this part so far. Okay, so far. Now, the limit as n goes to infinity of, I see a lot of n's in here. So we can multiply the 3 over n inside. That gives me 81 over n cubed, n to the 4th, times. What is this one here? This one, we gave you a formula. You go back to the previous section and find it out. It was n times n plus 1, all squared, actually over 2 all squared. That was the formula from the previous section. Minus, multiply the 3 over n inside. 3 times 18, 54 over n squared. And this one had a formula, n times n plus 1 divided by 2. Now we got a big expression to find the limit for. Limit as n goes to infinity. So let's see what we have here. We have, the first one we need to do is, I got 81 over n to the 4th times. This part is n squared plus n. When we square it, that gives me n to the 4th plus 2n to the 3rd plus n squared, all over 4. Minus, keep this the same. The top is n squared plus n all over 2. Let's see what we have. Limit as n goes to infinity. For the top one, you get 81 over 4 for this. I got n to the 4th plus 2n to the 3rd plus n squared, all divided by n to the 4th. Minus, we get number-wise 54 over 2 times n squared plus n all over n squared. And let's see what does that give us. So the limit as n goes to infinity, for the 81 over 4 stays the same. This one, when we evaluate the limit, you can either use L'Hopital's rule, or if you remember back from limits, this is simply 1 over 1 because they have the same exponents. So that would give us simply 1. Minus 54 over 2 times, same thing here, they have the same exponents, so the limit would be 1 over 1, which is also 1. So that's after we pass the limit. So the limit is gone now, no more limits. So now what we have 81 over 4 minus 54 over 2. Multiplying top and bottom by 2, that would give us 81 minus 810, 108 over 4. If we subtract that out, you get negative 27 over 4. And that gives us in return about negative 6.75. Now, notice something. Based on this result, what we did, we found this integral gives me exactly the area under the curve. That gives me exactly the area under the curve. When I did the right end point, I only got negative 3 point something, almost negative 4. And the other one I got negative 6.75. Kind of close, but not very close. If it happened when I did the right Riemann sum and I found, or I chose n to be 20 or 30, then I'll get way closer to this than just choosing n equals 6. So as we increase the number of subintervals, the closer the value, the estimated value to the actual value. So now, how we apply this integral? How do we apply them? Where do we apply them? Let's recall the area of the circle. Area of the circle is given by pi r squared, where r is the radius of the circle. And the area of a semicircle, in that sense, is 1/2 of that, 1/2 pi r squared. Okay, so if we take any a circle, the circle with center 0, 0 and radius r, so a circle like this, capital R. So the equation is x squared plus y squared equals r squared. That's the equation of the circle, the formula for 0, 0 as the center. So if I solve for y squared, so y squared is r squared minus x squared. So I want to get y by itself. It's plus or minus the square root of r squared minus x squared. Don't forget the plus or minus. So if I want to split this into two equations, one is plus and one is minus, so or y equals negative r squared minus x squared. So the top one is the plus case. So this is the case for y equals the square root of r squared minus x squared. And the bottom one, this one that I'm going to shade with red, that's the negative case. Y equals negative the square root of r squared minus x squared. So keep that in mind, it helps. So how do we apply all of this to calculus? Let's say we are asked to evaluate by interpreting each integral in terms of area. Of areas. So what we have, let's say we are asked to find the integral from 0 to 1, the square root of 1 minus x squared dx. So you can do Riemann's, not Riemann sums, you can do the actual sigma notation, but it will take a lot of time. But here we're going to just interpret this as an area. So this is actually asking us to find the area under the curve, this one, f of x, from x equals 0 to x equals 1. So how do we do that? So we have the function y or f of x is this. If we happen to square both sides, we get y squared equals 1 minus x squared. Adding x squared to both sides. What does that give me? It gives me a circle with center 0, 0, radius 1. So radius 1, 0, 0 at the origin. But notice, imagine you want to go backwards. So you want to solve for y. You would subtract x squared, then you did this. But wait, there's no plus or minus, there's only plus. This means this function that they give us only represents the one on the upper half plane, only the upper one. So this means, and they are saying, please go from x equals 0 to x equals 1. So this means they're only talking about this part. From 0 to 1, from x equals 0 to x equals 1. So this integral now represents the area of the shaded quarter circle. Shaded quarter circle. That's what this is. And so now how do I find the area of the core circle? Is 1/4 the area of the actual circle, pi r squared. And the radius here is what? It's 1. So the answer is simply pi over 4. And you can keep it like that. That's using how we interpret the integral as areas, and we found it. Another example, let's say we're asked to find the integral from 0 to 5 of x plus 1 dx by interpreting this as areas. So again, what we need to do is we need to graph the function. This is the function. So I have y equals x plus 1. I'm going to graph it when x is 0, y 1, y 0, x negative 1. So we go from 0 to 5. Say 5 is here, 90 degrees. So it's going to be all of this. That's the area I need to find out. Okay, so how do we find the area of this? What kind of figure is this? That's not a circle anymore or semicircle. This is a trapezoid. There are several ways to do this. One way is if you are able to find the area of the trapezoid. So that's the area of shaded trapezoid. The formula for the area of the trapezoid is 1/2 base 1 plus base 2 times the height. 1/2 base 1, where's base 1? This is base 1. This is base 2. And this is the height of the trapezoid. So the height, we know it's 5. We're done with that part. Base 1, how do I find base 1? Remember that was 1. Base 2, to find this base 2, the height itself, you substitute x equals 5 into the equation to find its corresponding y value, which is going to be 5 plus 1, 6. So that's 6. So now I got 1/2 times 7 times 5. So that's 35 halves, which is 17.5. Now students ask, what about if I forgot the formula for the area of the trapezoid? No problem, there's another way to do this. You can drop a height on this, and now you have two different figures. This one, which is a rectangle, and what's the area of this rectangle? It's length times width, means 5 times 1, 5. And we have a right triangle up there. This is 1, and remember the whole thing is 6, so this is 5. So the area of this triangle is 1/2, base is 5, and the height is 5. So 25 halves, that's 12.5. So all we have to do, add 5 and 12.5. That gives you 17.5. That's the area of the trapezoid in a different method. Now those integrals, the integral we have stated earlier, they have properties. We're going to see those properties, that they're very important of integrals, and then see how we apply them by going over some examples. So properties of integrals. The first property said, if you are integrating from a to b f of x dx, you are allowed to swap the bounds, make a b be a, but then what changes does that make to the integral is the negative sign. The next property, if you are integrating from a to a, from something to itself, this means there's no area under the curve, so it's 0. Next property, if you are integrating a function, nothing, just a constant c dx from a to b, that would give us c times b minus a. So the upper bound minus the lower bound. C is a constant. 4. If we are integrating a to b, a function plus or minus another function, all you get, a to b, the integral of the first one, plus or minus the integral of the second one. So in other words, you're allowed to split the integral. If you have 2, 3, 4 functions, as many as you want, as long as there's a plus or minus in the middle. But this does not work with multiplication. Just keep that in mind. Last property, if I'm integrating from a to b with a constant c times a function f of x dx, you can take the c out and integrate from a to b f of x dx. So you're allowed to take the constants out all the time. So let's see, how do we apply this? Let's say someone asks us to evaluate the integral from 0 to 1, 7 plus 3x dx. So how do we evaluate something like this? Well, we can first integrate, split this 0 to 1, 7 dx plus the integral 0 to 1, 3x dx. If you can see that. By using property number 4. Now, this looks like property 3 because 7 is a constant. So property said take 7 out and 1 minus 0. For the next one, by property, last property, you're allowed to take the 3 out. And now we have to integrate this. So how do I integrate this? As we did in the previous example, we have a function here, y equals x. This is the graph of y equals x. From 0 to 1, 0 to 1. What would that be? It's 1, 1, so it's 1/2 base times height. So that's 1/2, the area. So I got a 7 here plus 3, and the area of this is 1/2. So that gives us 7 plus 1/2, or 8/2. Okay, so that's what I have. The next one, as another really powerful thing to know, if we are integrating from a to b, f of x dx, we can go from a to c, f of x dx. In other words, you can find the area from a to, under the curve from a to c, plus the area from c to b, f of x dx. And that will give you the entire area from a to b, f of x dx, under the graph of the function f. How do we apply them? How do you apply this? Let the integral from 0 to 5, f of x dx, equals 12. And the integral from 0 to 3 of the same function is 8. We would like to find the integral from 3 to 5, f of x dx. To help me to do this kind of problems, always on the side I draw like a number line. They give me 0 to 5, the first one. So that's given. And they give me 0 to 3. So that's given. They want me to find this, 3 to 5. So based on that number line, this equals, you can go the whole thing 0 to 5 and subtract 0 to 3. So you go 0 to 5, f of x dx, minus the integral 0 to 3, f of x dx. What's 0 to 5? It's given 12. 0 to 3, it's given 8. So this would be 4. So this is 8, this is 4. The whole thing is 12. Let's look at another example similar to this. If the integral of f of x dx from 0 to 10 is 27. The integral from 3 to 10, f of x dx, is 18. And the integral from 0 to 10 to another function, g of x dx, is 16. Find, first one, the integral from 10 to 3, f of x dx. f of x dx. For this kind of problem, wait, I look at the first one 0 to 10, the next one 3 to 10. Oh, 3 to 10 is the closest to this one, 10 to 3. By the first property, it says if you want to swap the bounds, make it 3 to 10, f of x dx, you need to put a negative sign. And that gives us negative 18 because the other one was given 18. So that was one example on this. What about another one? What about if I'm asked to find 0 to 3, f of x dx? 0 to 3, f of x dx. So how do I do this? Let's see what we have. So they give me 0 to 10 and they give me 3 to 10. 3 to 10. So 3 to 10. So I want 0 to 3. So I want this. So all you have to do, go 0 to 10, f of x dx, minus the integral from 3 to 10, f of x dx. So 0 to 10 was given to us as 27. So 27 minus the other one was given as 18. So the answer is 9. A third part to this problem. What about if we are asked to integrate? Find the integral 0 to 10, 3 f of x plus 5 g of x, all dx. So how do we start with something like this? So to start with this one, first thing, based on one of the properties, we can split the sum into two integrals, plus the integral from 0 to 10. The bounds stay the same, 5 g of x dx. Now what about these constants, the 3 and 5? We take the 3 out, 0 to 10 f of x dx, plus 5 out, 0 to 10 g of x dx. Okay, now what we can do next is the first one is given to us 0 to 10. It was given as 27. So that's 27 here plus 5 times g of x. Don't confuse g of x with f of x. G of x was 16. So there's 16 here. And 3 times 27 is 81. And 5 times 16 is 80. So that gives us 116. So 161. And one other thing to talk about here in this section is the comparison properties of integrals. Comparison properties of integrals. So what do we have in the comparison properties of integrals? What do we use here? First one, if f of x is bigger than or equal to 0 and x between a and b, then the integral itself from a to b is going to be bigger than or equal to 0. So what this is saying, if the graph of the function falls above the x-axis, because 0 means the x-axis, then the area from a to b is going to be either 0 or above, 0 or more. So 0 like positive. That's what this is saying. Another one, if f of x bigger than or equal to g of x, that means if the graph of the function f is higher than the graph of g, and we are working over the interval a to b, then the integral from a to b, f of x dx, is bigger than or equal to the integral from a to b, g of x dx. 3. If small m, constant m, is less than or equal to the function and the function is less than or equal to capital M. So the graph of the function is bounded between these two numbers, real numbers, and x is from a to b, then the integral from a to b of small m dx is less than or equal to the integral of the function from a to b dx less than or equal to the integral from a to b m dx. And from here, if you remember one of the properties, if there's a constant here, we do the constant times b minus a. Keep this the same, a to b, f of x dx, less than or equal, capital M, another constant, b minus a. b minus a. So this is an important property here to know. And how can we use this, such a property? Let's say we are asked to estimate the integral from 0 to 1 e negative x squared dx. Just this one. Now, if we would like to integrate this or graph it or something, it's not going to be easy to do. It's not going to be a circle or half a circle or a trapezoid or any geometric figure we are familiar with. So what are we going to do then in this case? We are going to estimate it. That's what the question said. Try to estimate this. Estimate means either get an estimated value or find where the value of this integer could fall between what two numbers, what two possible numbers. Okay, so how we handle this one? If we happen to graph this function, the function f of x, e negative x squared. If we happen to graph this, so the graph would look like, I think, around this from 0 to 1. This is 1. So if we find f of 0, e to the negative 0, 0, that's 1. And f of 1 is e to the negative 1 square, which is e to the negative 1, or 1 over e. So that's 1 over e. And notice how the function is decreasing. So the function is decreasing. So over, first thing, over the interval 0 to 1, over 0 to 1, we know that the function is not going to go below 1 over e. It will never go below 1 over e. So the minimum m is 1 over e. That's the minimum value the graph can reach. And capital M is 1. That's the maximum point the graph can reach. As soon as you find the minimum and the maximum, so the graph will not go below 1 over e or above 1 or above 1. So in this case, what we do, we use the formula small m b minus a less than or equal the integral from a to b f of x dx less than or equal capital M times b minus a. A and b are given. This is a, this is b. So small m is 1 over e, 1 minus 0, integral 0 to 1, and the function was e negative x squared dx less than or equal capital M was 1, b minus a is 1 minus 0. And what does that give us? 1 over e less than or equal 0 to 1, e negative x squared dx, and this is 1. And if you like to find 1 over e on the calculator, that gives us around 0.367 less than or equal the integral 0 to 1, e negative x squared dx less than or equal to 1. So what I was able to do, I didn't know how to find the exact value for this integral up to the point where we are now in the course. We don't have enough tools to really find the exact value for that integral. But I was able to find a lower and upper bound on the integral. I was able to find where does the value fall. So the value of that integral is going to go between 0.367 and 1. So that's really good bound on the integral. Provided we are only working from 0 to 1. If you work from like 0 to 2, the value will be different, or the bounds will be different. So that's how we introduce, that's what integrals are about, and introducing them. In the next section, we're going to see more and more applications to integrals and how we work with them.